Hello, everyone. Today we're going to look at our last example of applications of derivatives. These are going to be called optimization problems. We're just going to look at some examples of these. All right. So our first problem is you have been asked to assign a 1-liter can-shaped right circular cylinder. We want to know what dimensions will use the least material. So we're going to ignore thickness of the material for the purpose of this question. We're going to note the formula for volume is going to be pi r squared h. And we're going to say this is also equal to 1,000. And we need a unit on this, so it's going to be centimeters cubed. So 1,000 centimeters cubed is the conversion for 1 liter. You're not going to be asked to remember that. And then for surface area, this is going to equal 2 pi r squared plus 2 pi rh. So again, we're going to ignore the thickness of this material, but what we want to do is find R and H such that the total surface area is as small as possible. But we still have to set aside pi r squared h equals 1,000 because we can't just ignore the volume. Okay, so let's draw a little bit of a picture. So let's say it looks something like this. So we have our cylinder, h is our height, r is our radius, so the diameter would be 2 times r. Okay. So we want a function of one variable. So what we can do is change one of the equations and then do a little bit of a substitution. So let's start with our volume. So volume equals pi r squared times h. But instead of volume, in this case, we know it's 1,000. So we'll just look at the 1,000 equals pi r squared h. And let's rewrite this. Let's solve for h. So if we have h, we'd have 1,000 divided by pi r squared. Okay. Now that we have one variable, we can plug it into our surface area. So if surface area is 2 pi r squared plus 2 pi rh, we plug it in for h. So we have 2 pi r squared plus 2 pi r, and then we have over 1,000 pi r squared. So just a little bit of a substitution there. All right. Let's see if we can simplify this. All right. So my left-hand side of this, 2 pi r squared wouldn't change, but if I multiply 2 pi r times 1,000 pi r squared, some things will cancel out for us. So my numerator, I'd have 2,000, 2 times 1,000. I'd have a pi r cancel in my denominator, so I'd have just divided by r, which makes this a lot nicer. Right. So now our goal is to find r greater than 0 to minimize a. Or SA, I'll call it. All right? So the first thing we want to do is find when f prime is equal to 0. So we're going to take the derivative of surface area, divide, or with respect to r. Okay? So we're going to take the derivative of the function we just found. So we'd have 4 pi r. Since 2 pi r squared, we move the 2 to the front, 4 pi. R squared becomes r. And then 2000 over r would just become plus minus 2000 divided by r squared. Okay. So now we want to set this equal to 0. So 4 pi r minus 2000 r squared. We can manipulate this equation. So we'd have 4 pi Let's see the best way to manipulate this. Right, we could minus the 4 pi r to one side and then multiply by r squared. That'd probably be the easiest. So this would be the same thing as 4 pi r to the third is equal to 2000. So again, what I did in this step, I subtracted 4 pi r to the other side, and then I have to multiply by minus 1 over minus r squared. So I have to get rid of that. Oh, sorry, let me repeat that. I subtracted the 4 pi r to the other side. Then I want to multiply by a negative r squared, and that's going to cancel out my r squared in that denominator. Okay? So now we just solve for r. We can do r to the third is going to be 2000 divided by 4 pi. I'm going to take the cubed root of both sides. And let's go ahead and plug that into a calculator. So we'd get r is about 5.42. Okay. So if we know r is about 5.42, we have to go ahead and plug that back into h. So we know h is equal to 1000 over pi r squared. So h is equal to 1000 divided by pi times 5.42 squared. So h would be 10.84. So with these, it's very important to say what our final conclusion is. So our final conclusion would be that 1 liter can that uses the least material is R is about 5.42 centimeters and H is about 10.84 centimeters. So I don't have space to fit that, but let's make sure we have our units on our R and our H. And it's all in centimeters here. Let's look at one more example. Let's say we have a rectangle inscribed in a semicircle of radius 2. What is the largest area the rectangle can be? And of course, we want to know what those dimensions are. So let's draw a little bit of a picture. So I have a semicircle from -2 to 2. And we want to put in a rectangle, right? So we know the best way to probably do this is if we start this origin here, and we want to find the point where it touches on this semicircle. We know the radius of this length has to be 2 because we have a semicircle. The equation for our semicircle, circles have the equation x squared plus y squared. In this case, it equals 4, since it equals r squared, so 2 squared would be 4, since the radius is 2. And that point, we could use the Pythagorean theorem. So if we call this length x, we don't know, this point would become x comma the square root of 4 minus x squared. So again, how I found that was I know that x, so we know that for our triangle we'd have x, and we have that 2, and we want to find that missing length. So how they're related, we use the Pythagorean theorem of x squared plus y squared, in this case equals 2 squared. So when we solve for our missing length, we'd have the square root of 4 minus x squared. So I recommend you practicing that and seeing where I got that square root of 4 minus x squared. Okay, so let's see what we know. We know the length of this rectangle should be 2x. We found the height from the Pythagorean theorem. It's going to be the square root of 4 minus x squared. So that makes the area. It's going to be 2x times the square root of 4 minus x squared. Because remember, area is just length times height. So let's call it a of x is equal to 2x square root 4 minus x squared. And we're looking at this on 0, 2. Because we need it to be 0, 2 just for domain reasons. If we have 4 minus the square root of x squared, if I plug in any number outside of 0 and 2, I'm going to have a negative square root, so it would be undefined. So it's just worth noting that we're on this closed interval of 0 to 2. Now we can go ahead and take our derivative. So we're taking the derivative of area with respect to x. So if we take the derivative of this area function, we are going to have to use the product rule. We have 2x as one of our functions, and the square root of 4 minus x squared is one of our functions, which again is going to actually use our chain rule. So as an exercise, I would like you to actually go ahead and write out that product rule and write out that chain rule. So that's what I'll be looking for on your notes, writing out this derivative. But for right now, it would be minus 2x squared over root 4 minus x squared plus 2 root 4 minus x squared. So again, I want you to show me why that is the derivative. Don't just take my word for it. Show me how to get from a to dA dx. Okay. And this is not defined when x is equal to 2, because then we'd have divided by 0. We can't have that. So not defined at x equals 2. Okay. So now we want to clear this denominator of square root 4 minus x squared once we set it equal to 0. So if I have minus 2x squared over root 4 minus x squared times plus 2 root 4 minus x squared equals 0, I want to multiply everything by the square root of 4 minus x squared. Right? So if I multiply everything by the square root of 4 minus x squared, I'd get minus 2x squared plus 2 times 4 minus x squared. 0 times the square root of 4 minus x squared would still be 0. So if I simplify this, I'd get 8 minus 4x squared. So I can subtract the 8 to the other side and divide by -4. So this is equals 0. This would simplify to x squared equals 2. I can square root both sides. So I'd get x equals plus or minus 2. But remember that it has to be positive. So x has to be positive at some length. So we can just say x equals the square root of 2. So that is the only one in the domain. So we want to find, since we have x now, we want to know what the a of root 2 is. So if I'm plugging in root 2 to my area function. So if I plug in root 2 to my area function, I'm going to have 2 times 2, or so let's go ahead and plug that back in, and we'd get 4. So I'm plugging back into here. So another way to think about it is if I plug in the root 2 to the x squared part, I'm going to have the square root of 2. I'm going to have plug in square root of 2 for the x part. So I'm going to have root 2 times root 2, which is 2. And then I'm left with 2 times 2, which gives me 4. So I want you to check this. And then let's also check those endpoints. So we said this was defined from 0 to 2. Let's just make sure those aren't maximum values. Most likely they're not going to be, because then we know our rectangle is flat. But a of 0 would be 0, and also a of 2 would be 0. All right. So we know those aren't the maximized area. So the area has a max value of 4. Okay. Okay. So we know this is, we want to know the dimensions, and we can go back to our length and our height. So remember, it's root 2 is the value of x. So if we want so when length is, we can plug that root 2 in. So 2 times root 2. And height, we plug in root 2 again. So if I'm plugging in root 2, I'm going to get square root of 2 squared. So we'd get root 2 again. So n height is root 2. Right. So here we find the derivative to set it equal to 0 to find the point at which, for x, that our value is maximized. Then we actually have to find that value. So we plug the root 2 back into the original area function. So it tells us that 4 is that maximum value. So when y is 4, that's our maximum value. So our max area is 4. And then we know what the x value is. We'd found that was root 2, where it hit its maximum. So we plug that root 2 back into our height and length from the beginning. And that's where we get the 2 root 2 and root 2. Okay. That's going to be it for today's class. Hope everyone has a great day, and I'll see you all next time.